recently, science news outlets have been reporting on a new paper describing a possible cosmic glitch in the universe. But what is this cosmic glitch? Well, to find out, I have one of the authors of the paper with me, Niayesh Afshordi, an astrophysicist and cosmologist from the Perimeter Institute for Theoretical Physics. Welcome, Niayesh.
Thank you very much for having me, Phil. It's good to be here.
So let's start with a simplest question. What is a cosmic glitch?
That's the best question, in fact. The simplest is always the best. So the idea of cosmic glitch is the idea that maybe gravity on cosmological scales, the largest scales that we can see in the universe, where speeds of objects, galaxies start to approach the speed of light, the gravity on those scales acts differently on smaller scales like within our galaxy or within our solar system. So there are basically two different theories of gravity that are in action on cosmological scales and on a smaller subcosmological scales, if you wish, or super horizon or subhorizon scales, where horizon is basically the largest distances that we can see. So the idea is that gravity is different, but gravity is different in the simplest possible way, in the sense that it's still the same theory, except that it has a different gravitational constant. So there's a gravitational constant that acts in our solar system, basically that tells us the force of gravity or strength of gravity. So, and that's a universal constant according to Einstein's theory of general relativity. So what we did was to ask, what if there's a glitch in the theory, in the sense that it looks like the same theory on larger scales and smaller scales. It's just that there's a slightly different constant that's in play.
So basically, you're just changing the value of the gravitational constant at different scales. So rather than like one constant, there's two constants. Is that right?
Exactly. There are two constants, and then where this glitch happens is the cosmological horizon scale. Basically, is the scale at which the speeds of galaxies or speed of the expansion of the universe starts to approach the speed of light.
Well, this sounds like a crazy idea. What would motivate you into thinking there is such a glitch?
That's an excellent question. And of course, these motivations can be complex and convoluted. But the clearest motivation that I've come up with over years is that the idea that Einstein's theory of gravity is unique is, and we've known about it for more than 100 years now, and it's been very experimentally successful in terms of all sorts of tests, from black holes to neutron stars to the solar system and so on. All these successes were on the scales where cosmic expansion hasn't been very important. On the scales where cosmic expansion, in fact, the universe is not basically a static, flat, more or less universe, but rather something that's very dynamical and violent in some sense. It's on those scales, Einstein's theory of gravity hasn't been as successful or not as much tested. And in fact, there's a mathematical theorem, or there are several mathematical theorems to that account, that Einstein's theory of gravity is a unique theory in a space which is technically called asymptotically flat, in the sense that if you want to describe basically gravitons, which are the spin 2 particles, there is a unique theory to do that.
These are the particles that would transmit the gravitational force if we assume gravity is like a quantum theory. Is that right?
That's right. So if you assume that gravity is a theory of geometry, and as quanta of geometry are gravitons, then Einstein's theory of gravity is a unique theory. But that uniqueness is only true if you ignore cosmology, if you assume that there is no expansion in the universe. In an expanding universe, that uniqueness evaporates. So there is no mathematical theorem. And then the idea is that what if indeed Einstein's theory of gravity is not unique, is not the right theory if you look at cosmological scales, because the uniqueness theorems we know are only valid on a small scales, or smaller than the cosmological scale. So that's one of the motivation. But there are others. There are certain inconsistencies that we see in understanding the expansion and structure formation in the universe. These are purely observational inconsistencies that you try to build up a model based on Einstein's theory of gravity to explain the fluctuations in cosmic microwave background, the rate of expansion of the universe as we observe, and how galaxies form in the universe. And we see that the same model doesn't seem to quite fit all of these observations. So that's another motivation,
Was
purely.
one of those, Niayesh, the Hubble tension, this idea that if we take two different measurements of the way the universe is expanding, they should give the same answer, but they don't. Is that one of the motivations?
That's certainly one of the experimental or observational motivations. It's far from the only one, and it's the idea that it's not that we measure the expansion of the universe in different ways. I mean, that should be just give you one answer. The problem is you always interpret these measurements in the context of a theory, because none of these measurements directly give you the expansion of the universe. You always basically, there are several assumptions that you have to make. And these assumptions, of course, some of them could go wrong. But one of them that's basically common between all these measurements is assumption of Einstein's theory of gravity. And it's a very foundational assumption. In some sense, this Einstein's theory of gravity is the most successful theory that we've had. So people try to kind of rule everything else out, like with 99.9% certainty, to go and then touch Einstein's theory of gravity. But at some point, this theory, I mean, as successful as it is, at some point it should fail. And we basically ask, what if this glitch is actually happening in theory of gravity as opposed to all the other assumptions that people might have made?
Right. So this glitch idea, is it related to like a quantum theory of gravity? It seems like it's some similarity to this theory called Ajava-Lifshitz gravity. Is that right? And can you explain what this theory is?
That's an excellent point. And in fact, what makes our approach unique in addressing cosmological tension is that often people just try to make up a model to explain the tension, and it's a space of theories is much bigger than a space of observations. So it's always possible to come up with multitude of theories to explain things. But the question is that can you actually explain more than one thing, or can you actually root your model in basically fundamental questions as well as experimental observations? And what's unique about a cosmic glitch is actually it wasn't something built up to explain the tension. It was a prediction from a quantum approach, in fact, to the theory of gravity. And in fact, it in some sense it predated the proposals, but there were basically these theoretical ideas that over the past 3 decades have been building up. And one of the things they have in common was this glitch that came up. So what's the idea? So the idea is that, again, maybe Einstein was not right. Maybe there is an ether. So there is a preferred frame. So at some level in the universe, now Einstein's great success was assuming that there are no preferred observers. And in fact, he used that as the foundation of his theory of a special and then general relativity. If different observers moving with respect to each other at some speed, they should see the same laws. In particular, the speed of light should be the same. But what if that success is only something that was an effective tool on a small scales, on a scales that we can see? But if you go to larger scales or more extreme environments, maybe even inside black holes, that is only an approximation. Maybe there are some preferred observers or some observers that the laws for them work differently compared to others. More concretely, maybe there is a cosmological ether which is subtle. It's very hard for us to notice it in this room, for example. However,
Yeah, actually, let me just interrupt. So the ether, let me see if I got this right. It was this substance that in the 19th century people assumed, water waves have to go through water, sound waves have to go through air. So they assumed light waves had to go through a substance, and they called that the ether. And then Einstein sort of did away with it as relativity. Is that a fair summary of what the ether is?
Absolutely. So that historically in the 19th century, there was this idea that all the waves have to propagate in a medium. And Einstein did away with that medium, said that in ideal environments, if you go into vacuum, for example, waves that exist in vacuum, like light, it seems that it can exist across a space, and even in extreme environments where there is very little air, light can propagate. So the idea was that there is this ether, or luminiferous ether, as it was called. And it turned out that there were experiments that were inconsistent with that assumption, at least in the standard context of classical physics. And Einstein's great genius was to do away with ether at the time and say that maybe, in fact, our notion of a space and time is not what we thought. There is no relative. Well, time is not absolute. Time is relative to the observers, as is a space. However, the speed of light is universal, and there is no ether. And that worked very well. However, Einstein's theory, which started as a special and then general theory of relativity, is a classical theory in the sense that it's not consistent with quantum mechanics. So it's not a complete theory. And in the last 20 or 30 years, people started to ask, what if what it takes to unify Einstein's theory or theory of gravity with quantum mechanics is to bring back the ether? Not necessarily the old ether of 19th century, but something more subtle that in extreme conditions, maybe very high energies or very low energies, you start to notice it. And in fact, observers or light or gravitons, gravitational waves, start to interact with it. Now, I should just add, if you bring that ether, then that actually allows for this glitch in gravity. You may see the same theory or same equations, but with different constants on cosmological scales compared to small scales.
Right. So is that Hojava-Lifshitz gravity? Is that basically similar, the same? Is that what we're talking about here, or is it different?
That's right. So Hojava-Lifshitz gravity is one of those ideas, but it's a broad class of ideas or theories put forward by Peter Hojava, who's the string theorist, interestingly enough, at Berkeley, who string theory is a competing model for quantum gravity. And nonetheless, Peter Hojava championed it. But there were others before him who had kind of considered this idea, like my colleague John Moffat or my friend John McGuejo. So this idea is the fact that there is a cosmological ether, in fact, has support or motivation from very different directions. Some from quantum gravity, like in Hojava-Lifshitz gravity, some from cosmology, the fact that we observe a homogeneous anisotropic universe on very, very large scales, even though light didn't have enough time to travel from one side of the universe to the other side of the universe. So there are kind of very different motivations for bringing back ether. And it may be that that's what it takes to explain some of these inconsistencies in current observations.
Right. So how does this idea of a cosmic glitch compare with the existing data? Presumably you've had a look at the CMB and various other features to see if it's consistent. Is it?
Yeah, so that was basically the main body of the work. I was done, the lion's share of this work was done by, in fact, an undergraduate student, Robin Wen, who, in fact, it happened during the pandemic, so I only met him like once here in Waterloo. And there were collaborators, Lucas Hert, who's in University of British Columbia, and Douglas Scott, who's a professor at University of British Columbia. So that was the lion's share of the work, was basically to look at this or kind of revive this theory of the glitch from the old ideas like Hojava-Lifshitz or earlier work that I had done with Ghazal Geshizjani, my wife, from like 20 years ago or so. So we kind of recycled this theory. We brought it back and said, okay, let's now compare it against the current data, and the data has really improved in the past 10 or 20 years. And indeed, that was the big surprise that we see. In fact, even if you ignore all the inconsistencies, the data, say the cosmic microwave background observation, prefers having a glitch at about the percent level compared to not having one. So this glitch is a very, very subtle thing. So if you don't look for it in, say, cosmic microwave background observation, it's very easy to miss it. In fact, everyone who had looked for it had missed it. Well, they hadn't really looked for it, basically. That's why they had missed it. But when we actually looked at this, which I think is a very simple extension of Einstein's theory of gravity, you're just saying it's the same theory, it just has a slightly different constant on large and a small scale. When we looked for it, we found it. And in fact, it's not just that we found it in cosmic microwave background observations, it also makes most of the tensions much milder. In particular, the rate of expansion of the universe becomes more comparable to what's observed from local measurements. And the structure formation, basically how much structures we have in the universe, it becomes more consistent between cosmic microwave background and galaxy observations that we have at.
Is that the S8 tension?
That's right. So that's been most recently called S8 tension. We called it a structure formation tension. But yeah, indeed, different people used to call it the sigmoid tension, S8 tension. But indeed, I think S8 tension is the most popular term for it.
So it looks like in both the cases, like this S8 of structure formation tension and the Hubble tension, we see this discrepancy from what we observe in the local universe and what we observe in great distances. And so would that support this idea that maybe there's different physics operating at these different scales?
Yeah, it's a little bit more nuanced than that, because you could there's a distance and time, and in fact, often people think about this as something that happens in time, like physics at the early times is different from late time. So there is this very popular idea, so-called early dark energy, that has been proposed, that maybe there was some early component of dark energy that was kind of messing things up early on and then disappeared now. It's a very contrived idea that is just kind of invented to address this. But the thing is, it's very hard to distinguish physics at different times from physics on different scales, because we really just things that are farther away are also farther in the past. But in reality, what our model was is, in fact, it depends on a scale, not time. So it's the same physics at early time or late times. It's just that you're looking at bigger scales when you look in the past, and small scales when you look here. So in fact, it's a scale dependence rather than time dependence, which is doing most of the magic here.
Niayesh, if we start mucking around with the theory of gravity, could this have any implications, like really big picture questions? I mean, I've done a series of films on the origin of the universe and what might have happened at the Big Bang. Could it affect something like that?
Yeah, absolutely. So bringing back ether is one of those most fundamental things that at the heart kind of changes our foundational notions of space and time. So as I said, basically doing away with ether was the very first thing that Einstein did to start his theory of relativity, and it was called the equivalence principle. So if you do away with that, the entire past century is in fact was based on the wrong premise. It's not that what we did was wrong, it's just that fundamentally some of the conclusions we have come to based on that premise might have been very different. Now, of course, the data that we could have explained, they are still there, but if you want to explore beyond that or extrapolate beyond that, things could be very different. For example, the assumption that there was a Big Bang singularity, that's based on general relativity. The fact that we couldn't explain in our theories why universe is homogeneous and isotropic, that could be very different if there is a fundamentally preferred frame, which is what kind of cosmology has been observing. In fact, one of the fundamental puzzles in cosmology was the horizon problem, and inflation was supposed to solve it. But if there is a preferred frame, then maybe there is no horizon problem. Basically, the universe does have a frame in which it wants to be uniform. So I think our notions of beginning certainly could be very different, and there are some hints that they are very different. But these are all extrapolations based on what we see. In reality, we have to make predictions and then look for clues, at least more clues that we have so far, to be sure about this.
Right. So let me come to that last question then, predictions. So you've analysed the data and it's looking good for your theories, so you claim. We'll see if other people agree. That's part of the scientific process. But the next most important part of that process is to make novel predictions for things we haven't seen yet. Is there any prospect for that?
Yeah, absolutely. So at the purely kind of pragmatic level, so we make a claim that we're measuring this parameter, and it's about 1%. And this we claim that there is essentially evidence for it at 2 to 3 sigma level. So that means that what we see could be pure noise, but there's maybe about 1% chance that it's pure noise. Now, is a percent really 1%, or maybe we are just too optimistic about our errors? That's, I guess, the judge is out on that. But the good news is that these experiments that are making measurements are going to get much, much more precise. So we have experiments like Euclid satellite by European Space Agency, DESI, which is a spectroscopic survey, is finding basically positions of millions of galaxies in 3 dimensions. And other experiments of the sort that they're going to measure these things much more precisely. So I think our forecast is that this measurement is going to be more accurate by a factor of 3 in the next 5 years or so. So at that point, then if this glitch is really there, then we should have a detection of it basically by traditional standards. And then at that point, you could decide that, okay, so if there is really a glitch, we should basically take maybe models of ether at the fundamental level, or even at the experimental level much more seriously.
Well, we shall wait and see what these satellites and other projects bring back, and maybe we can have you back on to discuss the results. In the meantime, thank you very much, Niayesh.
Thank you. I would love to be back.